Good evening, everybody. We have an interesting problem tonight where each of the coefficients is a function of a natural number k. I'm going to point out something, and I'll show you why here in a minute. But the sum of the roots, and there's three distinct roots that's posited in the instructions right here. The sum of the roots this function of k that's in front of x squared is actually minus the sum of the roots. Now, I'll tell you why that's important, and I can show you why real quick. We can call p of x this because we know that every every polynomial with real coefficients has can be factored. Maybe the roots repeat. It doesn't really matter right here, but I wrote these as x minus, what is that, delta, x minus rho, x minus omega. So that when you expand this out, you can see right here how minus the sum of the roots, right? Delta, rho, and omega would be roots of this polynomial. Okay, so even though this has a strange form up here, it still can split into linear factors. And some of these roots may repeat. It's not important. These aren't necessarily distinct. They would be distinct because they're specified to be distinct in this particular problem, but in general, they wouldn't necessarily be distinct. But what's important is minus the sum of the roots present right here as the coefficient of x squared. Okay? All right, so you see, now there's another thing that's important, and you'll see why this is important momentarily. We're given that the k that we're looking for is a positive integer, right? And so 1 plus or minus 1 will divide in, right? Now this is a little bit of a skyhook, I'll give you that. But plus or minus 1 are divisors of any natural number. So it turns out minus 1 does give you 0 back, and you guys can check that. I've written it out right here. And you can verify that if you want to, but it does. P at -1 ends up being 0. So -1 is one of the three distinct roots. So we already know what they are. What one of them is, we're not going to know what the other one is necessarily at the end of the problem, okay? But what this implies right here is that x plus 1 or x minus a minus 1 is a factor of this polynomial. And so I've written it that way right down here. Okay, p of x is equal to x plus 1. See how we have x squared here? And we were given that the sum of the roots is 125. Now, I didn't expand this out for you, but a minus sign will present right here, so this is how you would write that, okay? Now, notice that we've already used up, in other words, minus 1 was included in this count. We don't know what this count is, but minus 1 was included in this count, and so we have to correct that, and you can see right here, this is minus the sum of the roots. You see how I turned this around? That's minus the sum of the roots, but the square root of 125, you'll have to get rid of the minus 1 that was part of this sum, okay, right up here. Minus 1 was part of this sum now that we know that minus 1 is a 0, right, as a root. And that's why we had to correct it. You see this plus 1 right here? Okay, so that's really what's going on right here. We had to reverse this because of the minus sum of the roots condition. And also, this doesn't include the root minus 1 here. Okay, so that's why we had to add the 1 out here. It's a little subtle, but it's clear if you take a good look at it. Now, so what we have right here, folks, is k over 4 times the square root of k over 4 is equal to 125. But notice that that's the same as 5 root 25. See, folks, so by inspection, you can see what's going to work right here. What divided by 4 gives you 5, and it's both on it's the radicand and the coefficient out here. So this implies that k is equal to 20. Very slick problem in my humble opinion. Liked it a lot. Okay. And I guess now we could go back and find out what the roots were, but notice that the only root that we really know for a fact at this point is minus 1 is a root, and that was just by luck, sort of, so to speak. So that's kind of a skyhook. Maybe you can't rely on this in a competition. I don't know. but we would be sort of stuck here. I think you could maybe use, if you didn't discover that -1 was a root, you might be able to get by equating all the roots. You could equate them here. I don't know how far you would get or whether it would come out nicely, but you do know that the sum of two of them is the square root of 125. So if you didn't notice that -1 was a 0 of p of x, you still might be able to solve the problem. I'm not 100% sure, but this expansion here would be the way you would equate the coefficients. You could relate all these roots in their various forms. These are called elementary symmetric polynomials. You could relate them or set them equal. You could equate coefficients just by comparing that with the original problem. Okay, but in any event, that we caught a break with -1 being a 0, and so the final answer to this problem is 20. Find the value of k. That value is 20. Okay, good night.